In a multi-step process, one of the steps will be slower than all the others. The overall reaction cannot occur faster than the slowest step. This slowest step is called the rate-determining step. Consider these cars, represented by the bricks below, passing through two toll booths. Toll A is step 1, right here, to go from part 1 to part 2, and step 2 would be to go from part 2 to part 3. So which step, number 1 or number 2, is the slower step? The hint here is to look to see at which toll booth are cars getting backed up, because that's what's slowing down, in this case, the flow of traffic. Step 1 is the slow step, to get from 1 to 2 at toll A. Step 2 is much faster, to get from 2 to 3. In this multi-step process, which step, number 1 or number 2, is the slower step? So looking here, it looks like all the cars are getting backed up here behind toll B. So it's taking longer to get from 2 to 3 than it is to get from 1 to 2. So the slower step would be step 2, represented by toll B. So to go from here to here is the slow step. So if from here to here is step 1, and from here to here is step 2 is the slower step. So step 1 is fast, step 2 is slow. In a multi-step mechanism, the main idea about identifying the rate-determining step is this. The rate law for the overall reaction is equivalent to the rate law for the slowest or rate-determining step. This is because the overall reaction cannot occur faster than the slowest step, so the slowest step in any reaction mechanism is called the rate-determining step. All right, let's look through an example of a multi-step mechanism here. So this is a reaction NO2 gas plus CO gas produces NO gas plus CO2 gas. So the rate law for this reaction is found experimentally to be rate equals K times the concentration of NO2 squared. Okay, so carbon monoxide, CO, is necessary for this reaction to occur, but the rate of the reaction does not depend on its concentration. In other words, the rate of reaction is zero order with respect to CO. This suggests that the reaction occurs in 2 steps. Here's a proposed mechanism for this reaction. Step 1, where NO2 plus NO2, so 2 molecules of NO2, produce NO3 plus NO. In step 2, where NO3 plus CO produce NO2 plus CO2. Okay, and so because the CO is in step 2 and we know that the overall rate does not depend on its concentration, that's the fast step. And step 1 is the slow step. NO3 is an intermediate, so it is consumed in the second step. And again, to repeat myself, as CO is not involved in the slow rate determining step, it does not appear in the rate law. All right, so let's go through some questions here related to these proposed steps or this proposed mechanism. What is the molecularity of step 1? So there are 2 molecules, so the molecularity is 2. The rate law for step 1 would be rate equals K, and then there are 2 molecules of NO2, so K times concentration of NO2 squared. Step 2, the molecularity, it's bimolecular, so bimolecular. I guess I probably should have written that here too instead of just writing 2, because there are 2 molecules. It is bimolecular. Okay, and then the rate law for step 2, rate equals K times concentration of NO3 times concentration of CO. Okay, so it says, look at the 2 rate laws you wrote on the previous slide. I'll go back in just a minute. Which of these rate laws matches the rate law for the overall reaction that was found experimentally to be rate equals K times concentration of NO2 squared. So if we go back, it's the rate law that we wrote for elementary step 1. So this one right here. Okay, so if I go forward, which of the rate laws matches? It would be the one for step 1. So to summarize, the rate law for the overall reaction is equivalent to the rate law for the slowest or rate determining step. The rate law for the slow step, in the case of our example, the initial step, matches the rate law for the overall reaction, where rate is equal to K times the concentration of NO2 to the second power. All right, now let's go through a reaction mechanism example with a fast initial step. So we have a reaction that says 2NO plus Br2 produces 2NOBr. The rate law for this reaction is experimentally found to be rate equals K times concentration of NO squared times the concentration of Br2. Okay? Because intermolecular processes are rare, this rate law suggests a two-step mechanism. So what that means is that, see how these reactants, there are 3 of them? 2 of these and 1 of these have to combine to make 2 of these. So the combination of those 3 reactant molecules is very rare, which means this reaction is much more likely to happen in 2 steps. So here's a proposed mechanism for this reaction. Step 1 would be the first NO molecule plus Br2 to produce NOBr2, and that would happen very fast. And that step 1 includes the forward reaction with its K value and the reverse reaction, which has a K value that is inverse of the forward reaction. And then step 2 would take that intermediate NOBr2 plus the second NO molecule from the reaction to produce the product 2NOBr. And that would be the slow rate determining step. As we've been discussing, the rate law of the overall reaction depends upon the rate of the slow step. So going back to look at the slow step, I have 2 reactants, NOBr2 and NO. So I would get a rate law that looks like this. Rate equals what we're calling K2, or K for the second step, is concentration of NOBr2 times concentration of NO. But NOBr2 is an intermediate, okay? So it doesn't show up in the final rate law, and it doesn't show up in the one that we already know has been determined experimentally. So how do we find that concentration? It is a concentration that is very difficult to measure, and we'll discuss why on the next slide. Because NOBr2 is an intermediate that appears in both steps of the proposed reaction mechanism, it can react 2 ways. It can react with NO to form NOBr, our product, or by decomposition in the reverse reaction to reform NO and Br2 in step 1 of the reaction mechanism. Because that first step is very fast, that step quickly reaches equilibrium, where the reactants and the product are in equilibrium with each other. Equilibrium occurs when the rate of the forward reaction is equal to the rate of the reverse reaction. So we can write a rate law equation on the next slide to help us determine the concentration of NOBr2. Okay, so I'm going to rewrite step 1 of the reaction mechanism here just to refresh our memory. I suppose I don't need the concentration bars. So I have NO plus Br2. And the forward reaction has a K1 to produce NO Br2, our intermediate. And the reverse reaction, K minus 1. Okay. So the forward reaction, this one right here, I write my rate law based on those reactions. So here's that rate law where rate is equal to K1 times concentration of NO times concentration of Br2. Then my reverse reaction, which is this way, where NOBr2 decomposes, would give me this rate law, K minus 1 times concentration of NOBr2. Okay. So I just set those two rates equal because, again, that first initial step happens very fast and very quickly reaches equilibrium, and equilibrium is when the two rates are equal to one another. Then I just do some algebra to solve for the concentration of NOBr2, and I just get this ratio of the K values times NO times Br2 concentration. All right, so substituting the expression for concentration of NOBr2 that we just got in the previous slide, which you see here circled in green, and I'll circle again in yellow. I'm going to substitute that into my original rate law equation. And when I do that, I get this ratio of K values, which is just K for the overall reaction. Then I have 2 NO2, so concentration of NO2 squared, and then concentration of Br2. So there is the overall rate law for the overall reaction.